Today we're going to start talking about computing the PCA of high-dimensional vectors. This we will use in the following lectures to analyze the weather patterns across the world. So, what is PCA? It's a way to analyze covariance correlations between elements of the vector, and I'm not going to get into a lot of the details here, but the important thing for us is that there are two basic steps. The first step is to compute the covariance matrix. So this is a simple calculation, but it is a calculation that takes a lot of time and a lot of work for big data. At the end, it generates a single matrix, and then for that matrix, we need to compute the eigenvector decomposition. Now, this is something that is mathematically much more involved, but in terms of our big data work, it is not complicated. We just call a particular subroutine, and in terms of the time it takes, it's also a negligible amount of time. So what we're going to concentrate on here is how do you calculate the covariance matrix. So to compute the covariance matrix, we basically use the concept of outer product. So we take each vector outer product with itself and take the expected value of that, which gives us a matrix. And then we compute the expected value of the vector and take its outer product with the expected value of the vector. Okay, so that gives us a second matrix, and the difference is the covariance matrix. So if we're actually estimating this from data, then what we're doing is calculating the estimated expectation. And the estimated expectation is simply the average, in this case, of the outer products, and in this case, just of the vectors themselves. So one of the things that we have in big data almost always is that not all of the data is well defined. So for whatever reason, some of the entries in our data are not defined or clearly wrong, and we want to ignore them. So this is essentially the reason that to implement this operation, we're going to use RDDs of NumPy arrays instead of data frames. Okay, so this is because NumPy supports operations that are specifically tailored for vectors with non-entries. So what are those? So if we have a vector such that some but not all of the entries are none, and suppose we want to calculate the mean of the elements of X, if we use just NumPy mean, we will get none, even if there is just one none. On the other hand, if we use NumPy non-mean, it will remove all of the none elements and take the mean of the rest. So let's see an example. Here we see a vector of, I think, seven entries. 2 of the 7 entries are none. Okay, so this is the vector A. And if we take just the mean of the vector, as I said, you get as output none. Another thing that you might think of doing is to make all of the nones into zeros. Sometimes that's the appropriate thing to do, but in most cases it is not. So what this does is that it basically translates all of the elements that were none into 0, and then taking the average is basically taking the sum of all of these elements and dividing it by 7, because the 0 elements are also included. Finally, we have this operation non-mean, which takes all of the elements, removes the 2 elements that are none, and just takes the average of the rest. And in that case, we get 3, which I would argue is the natural, is the more natural result in this case. So suppose now that we have a vector that has nones, and we want to take the outer product of this vector with itself, then what do we get? Well, here is what we get. If we take the outer product of A with A, we see that the rows and the columns that correspond to the nans in A are also nan. Okay, so many of the entries will be nan, but if there's if this is a big matrix and the number of nans in the vector is not too big, then we still get a lot of useful information. So when is this a good idea to do? It's not always, as I said. Sometimes making them zero is better. But essentially, if you think that the process which removed the element is independent of the value of the elements, then it's a good idea. But here is a bad case. Suppose that the larger elements have a high probability of being none. In that case, non-mean will underestimate the mean, right? Because instead of basically, because those elements would actually move the mean a lot, so it might be, for instance, it might be that there is some kind of clipped value, maximum value that this sensor is allowed, and if it passes the value, then you get undefined. And what would be better is to just have the clipped value. So this and essentially any methods for dealing with nans have some kind of underlying assumption in them. They're not universally good methods, but they are often important because if you don't deal with the nans, then you might get significant biases. And if you deal with the nans by removing all of them, then you get other kinds of problems, like basically you remove whole parts of the data set that might actually be important. Okay, so how do we use these nans when we want to compute the expected value of the outer product? Well, we basically, what we do, we calculate two sums. One sum would be the sum of the matrices, so sum element by element, where the nans are mapped to 0. And the other is a matrix that has, for each entry, how many times it was not nan. Okay? So it might be different in different parts of the matrix. And then when we want to calculate the mean, we calculate S divided by N. So we divide element-wise each element from the matrix S by each element in the matrix N. So another trick that is going to be important for your homework is that we want to calculate both the expected or the average of the outer products and the simple average of the vectors themselves. And so, of course, we can do it. We can do each one of these things by itself. But here's a simple trick that basically lets us do both of them together without any additional coding. And then at the end, we just need to unpack the information. So the basic trick is very simple. Suppose that we have a d-dimensional column vector, x1 to xd. Okay, so so d in our case would usually be 365. And so these are the entries of the matrix. And what we're going to do is augment the vector. So the augmented vector, x vector prime, has a 1 in front of all of the x's. So now it is of dimension d plus 1. Okay, and it's just a simple transformation to do that. And now suppose that we take the outer product of x prime with itself. What do we get? Well, we get a matrix that has a special first row and a special first column, and then the rest of it is essentially the original matrix, the matrix of the outer product of x with itself. And here we just have a 1. And what we have here, if you'll check, is simply the vector x. Okay, and what we have transposed, and what we have here is the vector x not transposed. Okay, so Now, if we take these and we average many of these vectors, and remember there can be nans here and so on, that goes through, then what we get is a matrix where most of the matrix is the original expected value of x hat and x hat transpose. And in the first row and the first column, we have the expected value of x. So now we can just unpack that resulting matrix, and we have all of the things that we wanted. Okay, so and now we're going to just go quickly through this first notebook that that actually analyzes the climate data. What I will do here is I'll just go through some of the important cells. Most of the cells have to do with bringing the data from S3 or unpacking it and doing things like that I believe you can understand by yourself. But let's start with this. So this is data coming from NOAA, which is the North American Climate Organization, and it has a variety of measurements from all over the world. And these are the files that we put for you on just in the directory data weather on GitHub. So this first file is just how can you get the data yourself? You can FTP it from a site. This file is important. Basically, it gives you all of the explanations of what are the different fields, what are the different measurements, and so on. So this is a file that you'll have to read parts of it in order to understand what the data means. And then the last file is a file that is a table that describes the meteorological stations that are used in this database. Okay, so the measurement file is a table that looks essentially like this. It has in it the following columns: the station name, the station index, the measurement type. So this PRCP stands for precipitation, the year the measurements was taken, and the state in which this measurement is, because we're going to concentrate on stations in the United States, so they will all have a meaningful state. And values is essentially the data itself. It's packed in a particular way. Basically, it is a byte array, which consists of pairs of bytes that represent 16-bit floats. Okay, so that's how we represent them. But we represent them as byte arrays because that's how data frames, that's one of the types that data frames can use, and they don't understand directly how to use NumPy arrays. But the transformation is really just a type change. Okay, so here in this cell is basically all of the work of this notebook is done. And therefore, if you really want to see what all of the processing is, you need to go into into the lib directory, which has this and other functions that are used in the calculation, including the calculation of the PCA. So finally, once this is done, this is this table, or that basically this variable stat descriptions describes what are the different statistics that have been measured for a particular type of measurement, and includes things like the mean, the standard deviation, the bottom 1% and bottom 0.1%. And then here it has things like sum of the outer product that I told you about, and counts for the outer product. So count of the number of times that it's not nan, And then you have the covariance matrix, and then the decomposition of the covariance matrix into eigenvalues and eigenvectors. So basically, this is a summary of a lot of statistics for a particular measurement. And then we take these statistics and we use them to understand the data. Okay, so to summarize, we discussed how to compute the covariance matrix and the expectation matrix when there are none values. And we also showed you a little trick for how to compute the expected, the average outer product and just the average vector together. The details are in this function, and which calls other functions. And that is basically what we're going to do today. And we'll continue next time.